What if I told you that somewhere out there, hidden in the darkness of space, our sun has a twin? A second star that once shared the sky with the one we know. A star so faint, so distant, that we've never seen it. But the evidence suggests it might be real. Our solar system has always seemed unique. A single yellow star, 8 planets, a few dwarf planets, and billions of smaller objects drifting through the void. But here's the thing. When astronomers look at other star systems across the galaxy, they notice something strange. About 80% of them are binary systems. 2 stars, orbiting each other, locked in a gravitational dance that has lasted billions of years. Some estimates put it even higher. And yet, our sun appears to be alone. This raises an uncomfortable question. Why are we different? Why, in a universe where twin stars are the norm, does our sun have no companion? Some scientists believe the answer is simple. We're just one of the exceptions. The 20%. But others aren't so sure. They think our sun did have a sibling. A dark twin that has long since wandered away. And they gave it a name from ancient mythology. Nemesis. The idea first emerged in the 1980s. Paleontologists noticed something peculiar in the fossil record. Mass extinctions on Earth seem to follow a pattern. Every 26 to 30 million years, like clockwork, life on our planet faced catastrophic events. The dinosaurs 66 million years ago. The Great Dying 250 million years ago. The Late Devonian Extinction. Over and over, the pattern repeated. This was too regular to be random. Something was causing these periodic disasters. And 2 teams of scientists, working independently, came up with the same radical explanation. What if the sun had a companion star? A small, dim red dwarf or brown dwarf, orbiting at an enormous distance. So far away that it would take millions of years to complete a single orbit. And every time it swung close to the outer reaches of our solar system, it would stir up chaos. You see, beyond the orbit of Neptune, there exists a vast region called the Oort cloud. It's a shell of icy objects, comets and debris left over from the formation of the solar system. Trillions of these frozen wanderers, drifting in the darkness, held loosely by the sun's gravity. Normally, they stay out there, harmless and forgotten. But if a star passed through or near this cloud, its gravity would disturb these objects. It would send them tumbling inward, toward the inner solar system. Toward Earth. A sudden shower of comets. Some would miss us. Some would burn up in the atmosphere. But others would strike. And when a comet several kilometers wide hits a planet at tens of thousands of kilometers per hour, the results are catastrophic. Firestorms. Tsunamis. Dust clouds blocking out the sun for years. Nuclear winter. Mass extinction. The scientists calculated how far away this hypothetical star would need to be to create such a cycle. About 1 to 3 light-years from the Sun. For comparison, the nearest known star to us, Proxima Centauri, is about 4 light-years away. So Nemesis, if it exists, would be closer than any star we've ever detected. And yet, we've never seen it. How is that possible? The answer lies in the nature of the star itself. Nemesis wouldn't be a bright, blazing sun like ours. It would be dim. Incredibly dim. A red dwarf or a brown dwarf, emitting so little light that it would be nearly invisible against the backdrop of space. Brown dwarfs are sometimes called failed stars. They're objects that formed like stars, from collapsing clouds of gas, but never accumulated enough mass to ignite hydrogen fusion in their cores. They glow faintly, mostly in infrared, slowly cooling over billions of years. If Nemesis is a brown dwarf, it could be out there right now, and we simply haven't looked in the right place with the right instruments. The sky is vast. Searching for a dim, cold object that could be anywhere in a sphere surrounding our solar system is like looking for a single grain of black sand on a dark beach at midnight. But here's where the story gets more interesting. In 2010, astronomers discovered a peculiar object called Sedna. It's a dwarf planet, smaller than Pluto, orbiting in the outer reaches of our solar system. But its orbit is bizarre. Highly elliptical, taking about 11,000 years to complete one trip around the Sun. At its closest, Sedna is about 76 astronomical units from the Sun. At its farthest, nearly 1,000. Nothing we know of should have put Sedna in such a strange orbit. Some scientists suggested that a passing star, long ago, could have gravitationally perturbed Sedna into its current path. Others proposed a different explanation. A massive, unseen planet lurking in the outer solar system. This hypothetical world became known as Planet 9. But could Planet 9 and Nemesis be connected? Could they even be the same object? The debate continues. In recent years, surveys have searched for Nemesis without success. NASA's WISE telescope, which scans the sky in infrared, found no evidence of a Jupiter-sized object within 26,000 astronomical units of the Sun. No Saturn-sized object within 10,000 astronomical units. This doesn't completely rule out Nemesis. If it's smaller and colder than expected, it could still hide. But the window is narrowing. Some researchers now believe that even if our Sun once had a companion, it's long gone. Stellar dynamics in the early solar system were chaotic. Young stars often form in clusters, and gravitational interactions can eject members from the group. Perhaps Nemesis was never a true binary partner, just a passing stranger that briefly influenced our solar system before continuing on its journey through the galaxy. Others point to a different possibility. What if the mass extinction pattern isn't real? Statistical analysis is tricky, and some scientists argue that the 26 million year cycle is an illusion, a pattern our brains impose on random data. If there's no cycle, there's no need for Nemesis to explain it. And yet, the mystery persists. We still don't fully understand why mass extinctions happen when they do. We still find objects in the outer solar system with orbits that defy easy explanation. And we still live in a galaxy where most stars have partners, while ours apparently does not. The name Nemesis comes from Greek mythology. She was the goddess of retribution, the spirit of divine vengeance against those who succumb to hubris. It's a fitting name for a hypothetical destroyer, a dark star that periodically rains death upon our world. But there's another way to look at it. Mass extinctions, as terrible as they are, have shaped the history of life on Earth. After the dinosaurs died, mammals rose to fill the empty niches. Eventually, that led to primates. To humans. To you, watching this video right now. In a strange way, if Nemesis exists, it might be partly responsible for our very existence. The goddess of vengeance might also be a goddess of change, of renewal, of the endless cycling of life and death that drives evolution forward. For now, Nemesis remains what it has always been. A hypothesis. A shadow. A question mark hanging in the darkness beyond Neptune. We don't know if it's real. We don't know if we'll ever find it. But the search continues. New telescopes are coming online. New surveys are mapping the sky in unprecedented detail. And somewhere out there, hidden among billions of faint points of light, our sun's lost twin might be waiting to be discovered. Or perhaps it's not there at all. Perhaps we really are alone in a universe of pairs. Either answer would tell us something profound about our place in the cosmos. About how rare or common our solar system truly is. About the forces that shaped our world and everything living on it. That's the beauty of astronomy. Every answer raises new questions. Every discovery opens new mysteries. And sometimes, the most fascinating thing isn't what we find, but what we're still looking for. The search for Nemesis has pushed astronomers to develop new technologies and new ways of seeing the universe. When you're looking for something that barely emits any light, you have to get creative. Infrared telescopes became essential. Heat, after all, is easier to detect than the feeble visible light a brown dwarf might produce. But even infrared searches have their limits. The farther away an object is, the fainter its heat signature becomes. And if Nemesis is at the outer edge of its orbit, it could be almost undetectable. Consider the scale of what we're dealing with. The Oort cloud, where Nemesis would spend most of its time, extends perhaps 2 light-years from the Sun. That's almost halfway to the nearest star. At those distances, even our fastest spacecraft would take tens of thousands of years to arrive. We can't send probes. We can only watch and wait and hope that our instruments are sensitive enough to catch a glimpse. But there's another way to search for Nemesis. Instead of looking for the star itself, we can look for its effects. Gravity leaves fingerprints. If a massive object is out there, it will influence the motion of other bodies. Comets, asteroids, dwarf planets. Their orbits will carry subtle signatures of gravitational perturbation. By carefully tracking these objects, we might be able to deduce the presence of something we cannot see directly. This is exactly how Neptune was discovered in the 19th century. Astronomers noticed that Uranus wasn't moving quite the way it should. Its orbit showed tiny deviations. Something was tugging on it. Using mathematics, they predicted where the unseen planet must be. And when they pointed their telescopes at that spot in the sky, there was Neptune. A triumph of human reasoning. Finding an invisible world through pure logic. Could we do the same for Nemesis? Perhaps. But the math is far more complicated. The outer solar system is messy. Dozens of known objects, countless unknown ones, all pulling on each other in subtle ways. Disentangling these influences to find the signature of a single hidden mass is extraordinarily difficult. It requires precise measurements over long periods of time. Decades of observation. Patience that spans generations of astronomers. Some scientists have taken a different approach entirely. They've looked not outward but backward. Into the fossil record. Into the history of our planet. If Nemesis causes periodic extinctions, then the timing of those events might reveal information about its orbit. When was the last close approach? When is the next one due? The extinction that killed the dinosaurs occurred approximately 66 million years ago. If the cycle is truly 26 million years, then simple arithmetic suggests we might be close to another danger zone. Not tomorrow. Not next year. But geologically speaking, we could be entering a period of elevated risk. A time when the Oort cloud is being stirred. When comets begin their long fall toward the inner solar system. This is where the science brushes against something more visceral. Fear. The idea of Nemesis taps into deep anxieties about our vulnerability. We like to think we've mastered our environment. We've built cities, split atoms, sent robots to other planets. But against a cosmic bombardment, we are helpless. A large enough impact could end civilization. Could sterilize the planet. Could erase every trace that humans ever existed. And the terrifying part is that we might not see it coming. Comets from the Oort cloud approach from any direction. They spend most of their existence in complete darkness, invisible until they're almost upon us. By the time we spotted an incoming threat, we might have only months or years to respond. Maybe less. This existential dimension has given Nemesis a hold on our imagination that goes beyond pure science. It's become part of our cultural mythology. The Dark Star. The Death Bringer. The invisible hand that periodically resets the experiment of life on Earth. Whether it's real or not, Nemesis represents something true about our situation. We live in a universe that is beautiful but also dangerous. A cosmos that created us but could just as easily destroy us. Yet there's another side to this story. One that's often overlooked. Even if Nemesis is real, even if it does trigger periodic extinction events, life on Earth has survived every single one. For 4 billion years. Through ice ages and meteor impacts and supervolcano eruptions, life has persisted. It has adapted. It has evolved. The very fact that we're here to worry about Nemesis is proof that life is resilient. And we have something that no previous species has possessed. Awareness. We can look up at the sky and understand the dangers. We can build telescopes and track asteroids and develop technologies to deflect incoming threats. We are the first species on Earth with the potential to prevent an extinction event rather than simply suffer through one. That's remarkable. That's unprecedented in the 4 billion year history of this planet. The search for Nemesis, then, is more than just astronomical curiosity. It's part of humanity's larger project of understanding and ultimately protecting our world. Every dollar spent on sky surveys, every hour of telescope time devoted to cataloging faint objects, every graduate student squinting at data hoping to find anomalies. It all contributes to a growing shield of knowledge. The more we know about what's out there, the better prepared we can be. In 2016, researchers announced evidence for Planet 9, that massive unseen world in the outer solar system. The evidence came from the orbits of distant objects. Several of them showed a clustering, an alignment that would be statistically unlikely unless something big was shepherding them. The proposed planet would be about 10 times the mass of Earth. Not a star. Not even close. But still substantial. Still capable of influencing the outer solar system in profound ways. Some wondered if Planet 9 could be Nemesis in disguise. A smaller, closer version of the dark companion hypothesis. But the math doesn't quite work. Planet 9, if it exists, would orbit perhaps 400 to 800 astronomical units from the Sun. That's far closer than Nemesis would need to be to perturb the Oort cloud. And its mass is too small to explain the periodic extinction pattern. They appear to be separate mysteries. Separate ghosts haunting the outer darkness. The history of astronomy is filled with such ghosts. Hypothetical objects proposed to explain anomalies, some of which turned out to be real and others that faded away as better data emerged. Vulcan, the planet supposedly orbiting inside Mercury's orbit, was imagined to explain peculiarities in Mercury's motion. It was searched for throughout the 19th century. It didn't exist. Einstein's theory of general relativity eventually explained the anomaly without needing an extra planet. Will Nemesis go the way of Vulcan? It's possible. The periodic extinction hypothesis has faced significant criticism. More refined statistical analyses have cast doubt on the 26 million year cycle. Some paleontologists argue that extinctions are more randomly distributed than early studies suggested. If there's no cycle, there's no need for a cyclic cause. Nemesis becomes unnecessary. But science rarely provides clean, final answers. New data emerges. Old hypotheses are revived or modified. The Oort cloud remains poorly understood. We've never directly observed it. We infer its existence from the comets that occasionally fall inward. What else might lurk out there, in that vast reservoir of frozen debris? We simply don't know. And there are other anomalies that hint at hidden influences. The so-called Kuiper Cliff, for instance. The Kuiper Belt, a region of icy bodies beyond Neptune, seems to end abruptly at about 50 astronomical units. The population of objects drops off sharply, as if something has cleared them away. Some have suggested a distant planet is responsible. Or perhaps the Sun's birth cluster, long since dispersed, stripped away the outer material. Or maybe something else entirely. An explanation we haven't thought of yet. Every anomaly is an invitation. A puzzle waiting to be solved. And the outer solar system is full of them. Objects with inexplicable orbits. Gaps and clusters that defy simple explanation. A frontier that we're only beginning to explore. The Vera Rubin Observatory, coming online soon, will revolutionize our understanding of this region. Its wide-field surveys will catalog millions of faint, distant objects. If there's something big out there, something like Planet 9 or even remnants of Nemesis's influence, Rubin should find evidence of it. The next decade promises answers. Or at least, better questions. There's a philosophical dimension to all this that's worth considering. The search for Nemesis is ultimately a search for our origins. Where did we come from? Why is our solar system the way it is? What shaped the conditions that allowed life to emerge on Earth? These are not just scientific questions. They're the deepest questions we can ask. And every piece of the puzzle we uncover brings us closer to understanding our place in the universe. Think about what it means if Nemesis is real. It means our sun was born with a companion. For millions or perhaps billions of years, two stars traveled together through the galaxy, sharing the same cloud of gas from which they formed, dancing around a common center of mass. And then, at some point, they parted ways. Perhaps violently, through a close encounter with another star. Perhaps gradually, drifting apart over eons. Either way, the separation left scars on our solar system. Perturbations in the Oort cloud. Unusual orbits. Perhaps even periodic extinctions. Our solar system, in this view, is not pristine. It's battered. Shaped by violence and loss. The calm, orderly arrangement of planets we see today is the result of a chaotic history. Collisions. Migrations. Gravitational struggles. The sun, sitting peacefully at the center, is a survivor. And so are we. Now think about what it means if Nemesis is not real. It means our sun truly is alone. An outlier in a galaxy of pairs. This raises its own profound questions. Why are we different? Is our solitude significant? Did the absence of a companion star somehow favor the development of life? Did it make our planetary system more stable, more conducive to the emergence of complex organisms? We don't know. But both possibilities are fascinating. Both tell us something important about the universe and our place in it. This is why the search matters. Not because finding Nemesis would be dangerous or exciting, though it would be both. But because either answer enriches our understanding of ourselves. The universe is under no obligation to make sense to us. It wasn't designed for human comprehension. And yet, remarkably, we can comprehend it. We can look at points of light billions of kilometers away and deduce their composition, their temperature, their motion. We can peer back in time to the early universe and understand how galaxies formed. We can predict eclipses centuries in advance and send spacecraft to land on moving asteroids. This is extraordinary. This is what makes us special as a species. And it's what drives us to keep looking. To keep asking. To keep searching for dark stars that may or may not exist. Because the act of searching is itself meaningful. It's how we grow. It's how we become more than what we were. Nemesis might be out there. A cold, dim wanderer circling our sun in an orbit so vast it defies imagination. Or it might be nothing more than an elegant hypothesis that didn't survive contact with reality. Either way, the search has taught us something. About the outer solar system. About stellar dynamics. About the history of life on Earth. About ourselves, and perhaps that's the real gift of Nemesis. Not the answer, but the question. The way it forces us to look outward and inward simultaneously. To contemplate both the mechanics of celestial bodies and the fragility of existence. To hold in our minds the vastness of space and the preciousness of this one small world where everything we've ever known has happened. Consider for a moment the journey of a comet dislodged by Nemesis. It begins in the Oort cloud, frozen and still, where it has rested for billions of years. The sun from that distance is just another star. Bright, yes, but not dominant. Not the blazing presence we know. Then something disturbs it. A gravitational nudge. Perhaps from Nemesis sweeping past. Perhaps from a passing star or the cumulative tug of the galaxy itself. Whatever the cause, the comet begins to fall. At first, the motion is imperceptible. Years pass. Decades. Centuries. The comet drifts inward, accelerating slowly as the sun's gravity strengthens. It crosses the orbits of hypothetical planets. It enters regions where the sun's light begins to warm it. Ice sublimates. Gas escapes. A tail forms, streaming away from the sun, glowing in the solar wind. The comet becomes visible. Beautiful. A wanderer from the edge of everything, announcing its presence to anyone watching. If Earth happens to be in the wrong place at the wrong time, that beauty becomes destruction. The comet strikes at cosmic velocities. The energy released dwarfs nuclear weapons. The impact winter begins. Species that survived millions of years vanish in generations. The world changes irrevocably. But if Earth is elsewhere in its orbit, the comet passes harmlessly. It swings around the sun and begins its long journey back to the darkness. Another close approach in 10,000 years. Or 100,000. Or maybe never. Some comets are ejected entirely, flung out of the solar system to wander between the stars forever. This is the cosmic lottery we're part of. Have always been part of. Long before humans existed to worry about it. The dinosaurs didn't know what hit them. Literally. They looked up at the sky and saw a point of light growing brighter, and then there was fire, and then there was darkness, and then there was silence. 66 million years later, we dig up their bones and piece together what happened. We have the privilege and burden of knowing. Of understanding that the sky is not just beautiful but also dangerous. That the universe operates on scales that dwarf human concerns. That we are, cosmically speaking, temporary. This knowledge could paralyze us. It could fill us with despair. But it can also motivate us. Push us to build, to explore, to protect what we have while we have it. The astronomer Carl Sagan often spoke of Earth as a pale blue dot. A tiny mote of dust suspended in a sunbeam. Everything we've ever loved, every war ever fought, every symphony ever composed, every child ever born. All of it happened on that dot. And that dot is vulnerable. Not just to human foolishness, though that's dangerous enough. But to the indifferent physics of the cosmos. To rocks falling from the sky. To stars we've never seen. Nemesis represents this vulnerability. It's a symbol as much as a scientific hypothesis. The reminder that we are not masters of the universe. That forces beyond our control shape our destiny. That survival is never guaranteed. But symbols can be transformed. Nemesis was the goddess of vengeance. but she was also the goddess of balance, of justice, of the natural order reasserting itself. Perhaps that's a more useful way to think about what Nemesis represents. Not just destruction, but renewal. Not just death, but the clearing of space for new forms of life. After all, we owe our existence to mass extinctions. Without them, mammals would never have risen to prominence. Without the death of the dinosaurs, there would be no primates. No humans. No one to wonder about dark stars and the fate of worlds. The very catastrophe that destroyed one form of life created the conditions for another to flourish. This is the paradox at the heart of the Nemesis hypothesis. If it's true, if a dark companion star periodically devastates Earth, then that devastation is woven into the fabric of our existence. We are children of disaster, products of cosmic violence. The stars that threaten us are also, in a strange sense, our ancestors. It's a humbling thought, and a unifying one. Every creature on Earth, from bacteria to blue whales, shares this heritage. We are all survivors. All descendants of organisms that made it through the worst. That adapted. That found a way. This connects us not just to each other but to the deep history of life itself. For billion years of struggle and innovation and persistence. When we search for Nemesis, we're searching for our own story. Trying to understand the forces that shaped us. Trying to read the autobiography of life on Earth written in the orbits of comets and the patterns of extinction. The tools we use for this search are themselves remarkable. Consider what it takes to detect a faint brown dwarf at the edge of the solar system. You need telescopes that can see in infrared, because brown dwarfs emit almost no visible light. You need surveys that cover the entire sky, because you don't know where to look. You need computers powerful enough to process billions of data points, searching for the needle in an infinite haystack. You need generations of scientists building on each other's work, refining techniques, eliminating false positives, slowly narrowing the possibilities. This is the scientific enterprise at its best. Patient. Methodical. Collaborative. Spanning decades and continents. Thousands of people contributing small pieces to a puzzle that no single person could solve alone. The search for Nemesis is not just about finding a star. It's a demonstration of what humanity can accomplish when we work together toward a common goal. And the results, whatever they turn out to be, will belong to everyone. This is science at its most democratic. The knowledge gained from sky surveys and infrared observations isn't locked away. It's published. Shared. Debated. Built upon. A student in Mumbai can access the same data as a professor in Massachusetts. An amateur astronomer with a backyard telescope can contribute observations that professionals use in their analyses. If Nemesis is ever found, it won't be the triumph of one nation or one institution. It will be a human achievement. A milestone in our species' journey to understand the universe. And if it's never found, if decades of searching conclude that our sun truly has no companion, that too will be valuable. That too will advance our knowledge. In science, negative results are still results. They eliminate possibilities. They focus future efforts. They bring us closer to truth. The question of Nemesis touches on something even deeper than astronomy. It connects to how we think about ourselves. Are we special? Is Earth unusual? Is our solar system a cosmic outlier or a typical example of planetary formation? For most of human history, we assumed we were at the center of everything. The sun revolved around us. The stars were fixed in a crystal sphere. The universe was created for our benefit. Then Copernicus and Galileo and Kepler and Newton came along, and we learned we were wrong. Earth orbits the sun. The sun is one star among billions. We are not at the center of anything. This was humbling. But it was also liberating. It opened up the universe. Made it vast and full of possibilities. If we're not special, then perhaps there are other worlds like ours. Other beings asking the same questions. Other civilizations searching for their own dark companions. The Nemesis hypothesis fits into this larger picture. If most stars are binary, and our sun is not, then we are indeed unusual in at least one way. But unusual doesn't mean unique. There must be other singleton stars out there. Other solar systems that formed alone or lost their companions. The question is whether this matters for the emergence of life. Some scientists speculate that binary systems might be less hospitable to life. The gravitational interactions between two stars could destabilize planetary orbits. Planets might be ejected or sent plunging into one of the suns. The habitable zone, that Goldilocks region where liquid water can exist, might shift unpredictably as the stars orbit each other. Life, which requires stability over billions of years, might struggle to gain a foothold. If this is true, then our sun's apparent solitude might be a feature, not a bug. We might be here precisely because we don't have a second star stirring things up. The absence of Nemesis, or its distant exile to the outer reaches of the solar system, might be one of the conditions that allowed complex life to evolve. This is speculative, of course. We have only one example of life, our own, and drawing universal conclusions from a sample size of one is risky. But it's tantalizing. It suggests that the very things that make our solar system seem odd might be the things that made us possible. The universe, it seems, is full of trade-offs. Binary systems are common, but might be less hospitable to life. Singleton systems are rare, but might provide the stability life needs. Mass extinctions are catastrophic, but create opportunities for new forms to emerge. Comets from the Oort cloud threaten annihilation, but also delivered water and organic molecules to the early Earth. Everything is connected. Every feature of our cosmic environment, from the sun's solitude to the composition of the Oort cloud, has played a role in making us who we are. Nemesis, whether real or imagined, is part of this story. It represents the forces that shape worlds and the contingencies that determine which forms of life arise. This is why the search matters. Not just for practical reasons, though protecting Earth from impacts is certainly practical. But for philosophical reasons. For the simple, profound desire to understand where we came from and what kind of universe we live in. We are a young species on an ancient planet in a vast cosmos. We've been asking questions for only a few thousand years. We've been doing science for only a few centuries. We've been searching the skies with telescopes for only a few generations. In cosmic terms, we just woke up. We just opened our eyes. And we're trying to make sense of a universe that has been evolving for nearly 14 billion years. Nemesis is one piece of that puzzle. A small piece, perhaps. But every piece matters. Every question we answer opens up new questions. Every mystery we solve reveals deeper mysteries behind it. This is the nature of knowledge. It expands not by filling in blanks but by creating new spaces to explore. The story of Nemesis is, in many ways, the story of science itself. We observe something strange. Mass extinctions that seem too regular to be random. A solar system that seems too lonely in a galaxy of pairs. And we ask why. We propose explanations. We test them against the evidence. We refine or abandon them as new data emerges. This process is never finished. There is no final chapter. No moment when we close the book and declare that we understand everything. The universe is too vast, too complex, too surprising for that. But that's not a failure. That's the point. The search is the reward. The questions are as valuable as the answers. If Nemesis exists, we will eventually find it. Our telescopes grow more powerful every year. Our surveys grow more comprehensive. The darkness that hides our sun's twin grows thinner with each passing decade. Sooner or later, the evidence will become undeniable, or it will become clear that there's nothing to find. And if Nemesis doesn't exist, then we will have learned something equally important. We will have confirmed that our sun truly is alone. That the forces shaping our solar system are different from what we imagined. That the extinction patterns we thought we saw were illusions, or caused by something else entirely. Something we haven't thought of yet. Something waiting to be discovered. Either way, we will have grown. We will have pushed the boundaries of human knowledge a little further into the dark. We will have done what our species does best. Asked questions. Sought answers. Refused to accept ignorance as permanent. Nemesis began as a name for vengeance. A dark goddess punishing human pride. But perhaps we should reclaim the name. Make it mean something different. Let Nemesis stand not for destruction but for the challenge that drives us forward. The mystery that keeps us searching. The unknown that makes knowledge meaningful. Out there, beyond the planets, beyond the Kuiper Belt, beyond everything we've ever touched or seen up close, the Oort cloud waits in silence. Trillions of frozen objects, circling our sun at distances we can barely comprehend. And somewhere in that vastness, something might be moving. Something faint. Something cold. Something that has been there since the beginning, shaping our history in ways we're only starting to understand. Or perhaps nothing is there at all. Perhaps the darkness is just darkness. Empty space extending to the next star. We don't know yet. But we're looking. And that's what matters. That's what makes us human. Not the answers we possess, but the questions we dare to ask. Not the light we stand in, but the darkness we're willing to explore. Nemesis may be real. Nemesis may be myth. But the search for Nemesis is undeniably real. And in that search, we find something more important than any star. We find ourselves.